integral over the limits of x and y directly, right? And order of the integration doesn't matter whether we integrate with respect to dx first or with respect to dy, the value of the integral will be same. This was the first Fibonacci theorem for the rectangular region, and then we discussed second form of Fibonacci theorem, that was the stronger version. And the stronger version says that if we have two types of region, first region was when we have the region bounded between two constant values of x and two curves y is equals to g1 to y is equals to g2, then the first formula we will apply, and whenever we can bound the region between two functions of y and constant value of y, we will apply the second formula. So we have seen one example in the last lecture. Let us start one more example today of the same type, and then we'll go for the change of variable method. Question is that changing order of the integration. So question is that evaluate the integral 0 to 2 y by 2 to 1 e power x square dx dy. So this integral we want to evaluate. The method is we need to apply Fibonacci theorem essentially. So let us note first that the function e power x square does not have the antiderivative. Note that e power x square does not have antiderivative. So therefore we cannot evaluate this integral directly, because essentially we are not able to integrate this function with respect to the x variable. So therefore what we do is we will change the order of integral, and we will first integrate this function with respect to y and then with respect to x. So therefore we shall change order of the integral. So to change order of the integration, first we have to look at what is the region, right, over which we are integrating the function. So let us first draw the region in the xy plane. So in the xy plane, what are the limits? Limits is limit of y is 0 to 2, and the x limit is from x equals to y by 2 to x equals to 1, right? That is the limit of x. So if you draw this region, the graph value of y is between 0 to 2, and the line we are getting is y equals to 2x and x equals to 1. So y is equals to 2x is something like this, and the second line we have is x equals to 1. So this is line x equals to 1. So what will be this point? Here we have x is 1, and since it is on the line y equals to 2x, the value of y is 2 times x, so that will give us the point 2. So our region is between y is equals to 0 to y is equals to 2, right? Y is equals to 2 line. And between x equals to y by 2 to x equals to 1. So that means our region essentially is this triangular region, and this is our region R. So if we want to change the order of the integral, what we need to do, we need to find two constant values of x, and we need to find functions y is equals to h1 x2, y is equal to h2 x, right? So let us do that first. So if you see the region, we can see that the constant values of x which bounds the given region are 0 to 1, right? So x equals to 0, that is this line, to x equals to 1. So these two lines bound the region, so they are these limits. And now on the other side, whatever equation we have, that equation will convert as a y as a function of x. So if we convert this line which bounds the region, so that will be y as a function of x. Already it is given y is equals to 2x, and the other thing is y equals to so this line bounds the region, that is y equals to 0. It is the x-axis. So since we are in this direction, the below line will come here, y is equals to 0 to y equals to 2x, right? So what we have done is, based on the given limits of the integral, we identified the region, and then we converted the region into the other variable constant limit and other variable function. So now let us write down that. Therefore our region will become the points xy such that the value of x is between 0 and 1, and the value of y is between 0 and 2x, right? So now we integrate the function. It will become, the original function was integral was this one, integral y by 2 to 1 e power x square dx dy. Now we change the order of the integral. So order of the integral means, instead of dx dy, now we have dy dx. The limit of y is from 0 to 2x, and limit of x is from 0 to 1, right? So since the original integral we were not able to integrate, we have changed the order of integral by finding the limits of the integral. So now what we will do is, we will integrate this function if it is possible. So we can see that e power x square function is constant with respect to variable y. So that means it will come out of the integral, and then integral of 1 is y, and limit of y is from 0 to 2x. And whatever this term we will get, that we will integrate with respect to dx. So we simplify this, then this will become 2x minus 0 is 2x times e power x square. So the earlier function e power x square does not have antiderivative, but now we can see that 2x e power x square has the antiderivative, and that is nothing but e power x square, right? Because when we differentiate the function e power x square, we will use the chain rule, so it will become 2x e power x square. So finally, when we substitute the limit, we get the value e minus 1. So sum of the integral, when we are not able to integrate the function directly, order of integration changing helps to evaluate the given integrals. So this is the method which we discussed, the Frobenius two forms. This was the stronger form of the theorem. Today what we want to discuss is change of variable in the double integrals. Change of variable we already know from the single variable function. When we have y is equals to f of x, we can change the variable x by t or t square and so on. So same method we want to discuss for the double integral. So here, since we have two variables, to evaluate the integral, we need to substitute the variables. So let us discuss first the general case, and then we'll discuss the special case of polar coordinates. If we want to change variables, x and y as a functions of u and v variable. We can do that whenever these functions so our functions are basically x as a function of u and v, and y as a function of u and v. Right. So these functions have continuous partial derivatives of first order. So x and y should be differentiable with respect to u and v essentially. So, so we use the notion of Jacobian. Which is defined by Jacobian will denote by J, that is a del xy. We are changing the variable xy in terms of u and v. Right. So this is essentially a 2 cross 2 determinant because this is two variable function. So we differentiate x with respect to u, and we differentiate x with respect to v. Then we differentiate y function with respect to u and y function with respect to v. Right. So whenever we want to change the variable xy as a variable u and v, we will find this determinant which is known as the Jacobian of variable change from xy to uv, right? And then we substitute this Jacobian into integral. So the integral will become, so suppose our original integral is integral over r fxy into dx dy. Then this integral we substitute all these values, so it will become double integral over t. Now t is a corresponding region in uv variable. So instead of x we substitute the function phi uv. In variable y we substitute psi uv, and then this Jacobian will take positive value of that, so we take modulus of that and du dv, where t is the corresponding region in the uv plane. So r is the given region in xy plane. When we substitute the variable, we get corresponding region in the u and v variable, so that is in the uv plane. So let us see what is the particular case of the polar coordinates. This is a particular case of change of variables. So we know that whenever we use the polar coordinates are x equals to r cos theta, y is equals to r sin theta. So what we'll do first is we know these functions, right? This is x r cos theta, y r sin theta. So next thing is finding the Jacobian. So Jacobian is the partial derivative of xy with respect to the polar coordinates r and theta. So here the Jacobian will become Jacobian is the partial derivative of xy with respect to our variables r and theta in this case. So that is basically del x by del r, del x by del theta, del y by del r, del y by del theta. Right. Whenever we substitute the values here, so partial derivative of x with respect to r is cos theta, x with respect to theta is minus r sin theta, sin theta, and this one is r cosine theta. So now what will be this determinant? This is r cos square theta minus r sin square theta. So essentially the Jacobian is r, because cos square theta plus sin square theta is 1. So for the change of polar coordinates, whenever we do, we will take the Jacobian to be r for every example of the polar coordinates, and then we'll identify what is this integral, right, in terms of the Jacobian. So here the integral will become so fxy dx dy will be integral over t, x is our r cos theta. Instead of x we substitute r cos theta. Instead of y we substitute r sin theta times modulus of the Jacobian. So r is the radius. So radius is always positive, right? So that means we just substitute r and dr d theta. And what is t here? Where t is the region in the r theta plane. So basically in r theta variable, whatever region we are getting in terms of r and theta. So let us take some example in the polar coordinates. So we want to evaluate double integral over r 3x plus 4y square area integral, where r is the region in the upper half plane bounded by the circles x square plus y square is equals to 1, and another equation is x square plus y square is equals to 4. So first question is, suppose this is given as an example, then there are three methods we discussed so far to solve this problem. So first method is whether the region is rectangular. So let us first draw the region. So the region is in the xy plane, and here we know that the region is essentially the upper half plane, that means above x-axis, and it is bounded by two circles. So first circle is the unit circle, that is x square plus y square is equals to 1, and second circle has radius 2. So this is basically x square plus y square is equals to 4, and it is in the upper half plane. Region is bounded by these two circles. So this is our region over which we are integrating the function. So clearly we will not apply the Fubini's first theorem. To apply the Fubini's second theorem, we need to divide the region into either constant limit of x or constant limit of y. So that is one of the methods maybe we can apply here. But why we are applying now the third method, which is change of variable, is that because our region is given to be circles. So we know that whenever we have a circle, that circle equation we can convert in terms of r and theta. So depending on what question is given, whether the function is in terms of x square plus y square or the region is in terms of x square plus y square, we shall decide that we will be able to solve this problem by change of coordinates by the polar coordinates, because the region is bounded by circles. So let us see if we can apply this method of the polar coordinates or not. So given region is the set xy such that y is non-negative and the value of x square plus y square is between 1 and 4. So if we change these integrals, if we substitute x equals to r cos theta and y equals to r sin theta, the corresponding region in r theta form will be, r theta plane will be, so new region will denote by t. So that is the point r comma theta, where, so what will be the limit of r? The region is bounded between x square plus y square is equals to 1 to x square plus y square is equals to 4. So what is x square plus y square? X square plus y square is r square. So that means our region is bounded between 1 and 2, right? Because r square is between 1 and 4, right? So 1 less than r less than 4. And what is the limit of theta now? So if we have a full circle, then the limit of theta is between 0 to 2 pi. But we have half circle here. So that means our limit will be half between 0 to 2 pi. So this line we have theta is 0 and along this line we have theta is pi. So limit of theta that is coming from y greater than equal to 0 is between 0 and pi. If our region is in the first quadrant, then limit of theta will be from, what will be limit for the first quadrant? Limit of theta, so we know that in the first quadrant we have limit of theta is from 0 to up to the positive y-axis. That means it is from 0 to pi by 2. So depending on what region we are given, we will decide what is the limit of r and theta. Yeah, any doubt?
सर R 1 to 2 होगा ना सर, यहाँ पे 4 लिखा है.
Yes, I have done mistake. Correct, you are right. So r is between 1 to 2 because our r square is between 1 to 4. Yeah. So thank you for the correction.
Okay sir.
So now we will use the formula of the integral. So formula of the integral we have denoted as this formula. So in the function we substitute x equals to r cos theta, y is equals to r sin theta, and instead of dx dy we substitute r dr d theta. So therefore the given integral, which is double integral over r 3x plus 4y square area integral, will become double integral over t of the function 3 times x is r cos theta plus 4 times y, which is r sin theta square, times the Jacobian is r times dr d theta. And what we know is limit also we know, limit of r is between 1 to 2. So that is the first limit. First is dr, and then we have limit of theta. Limit of theta is from 0 to pi. So now let us integrate this function. So if we integrate this function first with respect to r variable, then what we'll get is this is 3r square cos theta. So the integral will be r cube cos theta, because the integral of r square is r cube by 3 with respect to r variable, and the second variable will be 4r square 4r cube sine square theta. So that will become r power 4 sine square theta as the integral, and limit will be 1 to 2. Limit of r is between 1 to 2. So just check that if I have done any mistake, verify it. And if it is correct, then what we will do is we will substitute the limit of r. So if we substitute the limit of r, then r cube, where r is from 1 to 2, that means it is 8 minus 1. So we get 7 cosine theta plus r power 4. R is from 2 to 1. So it is 15 sine square theta d theta. So now this function we need to integrate. So sine square theta, we will use the trigonometric formula. Sine square theta is 1 minus cos 2 theta by 2. So this will equal 0 to pi 7 cosine theta plus 15 by 2 1 minus cosine 2 theta, integrating with respect to theta. So essentially it will be 7 sine theta plus 15 by 2 integrating with respect to theta. 15 by 2 theta minus 15 by 2 times integral of cosine theta is cosine 2 theta is sine 2 theta by 2. So this will become 15 by 4 sine 2 theta. The limit is from 0 to pi. So now we know that the sine function and sine 2 theta function are 0 at the value theta is 0 and theta is equals to pi. So essentially we need to find only in the limits of this term. So theta is from 0 to pi, that means this will be 15 by 2 times pi. So this is one of the example which is in terms of the polar coordinates. So change of variable from xy to polar coordinates r theta using the Jacobian, finding the limits in r and theta. And the reason why we are doing this is because our region is circular region, right? So that is the reason why we are applying the polar coordinates here. So now next example which we want to discuss is in terms of variable other than polar coordinates. So question is that evaluate the integral 0 to 1 minus x square root x plus y and y minus 2x square dy dx. So let us first find out what is the region of the integral. So here let us go go to the next PDF. So here the region of the integral is from x equals to 0 to x equals to 1. And the limit of y is from y is equals to 0 to y is equals to 1 minus x, right? So that is the limit of the region here. So let us draw the region in xy plane. It is bounded by x0, y0 and x equals to 1. And this line. So this line is basically x plus y is equals to 1. So x plus y is equals to 1 is this line. So our region is bounded from by y-axis, x-axis, x plus y is equals to 1 and x equals to 1 line. So that will be essentially this region. So the region is triangular region. The question is if we can solve. Of course, the Fubini's rectangular region theorem we cannot apply. So we need to apply either Fubini's stronger theorem or change of variable. If we apply the Fubini's stronger version, then we need to integrate this function square root x plus y, right? And the function square root x plus y is not easy to integrate. Rather, if you substitute the variable x plus y is t, let us say x plus y is t or some variable u, let us say, and if you substitute y minus 2x is equals to v, then our function will become square root u v square. And such a function is easy to integrate in variables u and v rather than integrating x plus y square root and y minus 2x square. So in the polar coordinates, what we have done is, depending on the region, we substituted the variable because the region was circular. But here, depending on the function, whether we are able to easily integrate it given the function or not, depending on that we are substituting the variables. So we substitute these. So we are substituting u equals to x plus y and v equals to y minus 2x. So first thing we need to check is, we need to check the Jacobian. And Jacobian, usually we substitute x equals to r theta, x equals to r cos theta, y equals to r sin theta. That means xy we need to convert in terms of u and v. So if we use elimination method for these two equations and convert x and y in terms of u and v, then what we get is x equals to u by 3 minus v equals minus v by 3 and y is equals to 2u by 3 plus v by 3. So just verify that this is correct or not. So basically we eliminated x and y from these equations. X plus y is equals to u and y minus 2x equals to v. So now our x and y variables are converted into u and v variables. So x and y are function of u and v. So we can find Jacobian. So Jacobian matrix will be Jacobian determinant will be J is equals to, we are converting x and y into u and v variable. So that means we have del x by del u, del x by del v, del y by del u, del y by del v. So this is a 2 cross 2 matrix and determinant of A and A transpose is same. So that means this x row we take uh, dx by dt, dx by dv, row wise or column wise, it doesn't matter. So now the partial derivative of x with respect to y, u will be 1 by 3. Similarly, partial derivative of x with respect to v will be minus 1 by 3. Right. Similarly, y with respect to u is 2 by 3, y with respect to v is 1 by 3. So let us substitute all these 4 values here. So we get 1 by 3 minus 1 by 3, 2 by 3, 1 by 3. And then we find this determinant. So it will be 1 by 9 minus plus 2 by 9. So that is 1 by 3. So finally, now we got Jacobian. So therefore, double integral fxy dx dy will be the integral over t f of x. X is u by 3 minus v by 3. Y is 2u by 3 plus v by 3 modulus of Jacobian du du. Right. So that will be nothing but double integral of our function is square root x plus y. So x plus y is sum of these two, and x plus y we know that it is u. Alright, so it will become square root u times v square. Modulus of Jacobian is 1 by 3 du dv. So what we have not done so far is we have not found the region T. So let us find the region T now. So equation in xy plane, we need to find the corresponding equation in uv plane. So what are the equations we had here? Our equations are x plus y is 1, y is 0, x is 0 to x equals to 1. Right. So let us find out this region. So our line x plus y is equals to 1. So if you substitute the values here, then our x and y is this. So whenever we take x plus y, what we will get is we get u only, right? The sum of x plus y is u. So x plus y is equals to 1 will become u is equals to 1. Similarly, x equals to 0. So x equals to 0 will gives us this term is 0. So this is 0 means we have the equation u is equals to v. So So whenever x is 0, we have u equals to v. And the third equation we have is y is 0. So y is 0 means v is equals to minus 2u. These are the three lines which bounds the given region. So let us draw the given region. So that is given as, this is our u axis, this is v axis. What are the lines? Lines are u is equals to 1, u is equals to v. This is our line u is equals to 1. Then x equals to y line, that is u is equals to v. And the third line is v is equals to minus 2u. So v is equals to 2u, we know v is equals to minus 2u will come. So this line is v is equals to minus 2 times u. So our region is bounded by these three lines, that is essentially this region. So now let us substitute this limit in the integral. If we substitute this limit in the integral, what we will get is, therefore the integral 0 to 1 minus x plus y minus 2x square dy dx will become integral. So the constant limit of u is between u is equals to 0, that is v axis, from u is equals to 1. U is 0 to u is 1. So now we are applying this stronger version of the Fubini theorem. So the above curve is u is equals to v, and below curve is v is equals to minus 2u. So that means our integral will become integral v is equals to minus 2u to v is equals to u. Right, so we converted in terms of u function, and then we know the integral is square root u v square, Jacobian is 1 by 3 du dv. So this is 1 by 3 times square root u v square du dv. So this we can simply evaluate now, because now we have limit of the function, and we also know the functions are powers of u and v. So first we integrate this with respect to v, we get v cube by 3. The limit is so essentially when we substitute this limit, we get the value to be 1 by 9 is integral 0 to 1 square root u times u cube plus 8u power 3 du. Because one, right, and then finally this turns out to be this is the integral of one variable, and we can easily check the value is 2 by 9. Right, so this is one or two examples which we wanted to discuss regarding the change of variable of the function.